It is 3:30, at least in my version.
Yes. Yeah, you can start, Manoj.
Okay. Welcome to this seminar. Today's speaker is Sudeshna Roy, and she will talk about graded components of local cohomology modules 2. Okay. Sudeshna, please.
Thank you, sir, for the introduction, and good afternoon, everyone. Today, I would like to talk about the behavior of graded components of local cohomology modules. This is based on a joint work with Professor Hutun Purakar. In the first part, Professor Hutun Purakar studied the behavior of these graded components extensively in a certain setup, and in this part, we extended some of those results to a wider framework. So these local cohomology modules in recent years is a fundamental tool in both commutative algebra and algebraic geometry. But despite of efforts of several authors, their structure is still quite unknown. And the reason behind that is they are rarely finitely generated. Although they are finitely generated over the ring of differential operators, which makes them manageable, and so that's why some finiteness properties have been obtained over regular rings in characteristic 0 using the theory of D modules. So for our work also we have used theory of D modules. So let's start with some basic the definition of local cohomology modules. So let C be a commutative Noetherian ring and ideal in C. It is a finitely generated C module. So throughout this talk, I will be assuming C to be a commutative Noetherian ring. So by gamma I of L, I am denoting the collection of all elements in L which are annihilated by some power of I. Gamma I denote the I-torsion functor. One can check that this is left exact. The ith right derived functor of gamma I that will be denoted by HII, and that is referred as the ith local cohomology functor. So if we apply this functor to L, then we will get the ith local cohomology module of L with respect to I. Let T be any standard deviation Noetherian ring, and T plus denote its irrelevant ideal. L plus B its L is a finitely generated graded T module. Then several authors have studied the ith local cohomology module of L with respect to T plus, and it is observed that they are particularly well behaved. There are several applications of these local cohomology modules in the study of Hilbert coefficients, associated graded rings, series algebras, and many more. And it is known for long that its graded components are finitely generated T0 module, and for large values of U, they vanish. And this vanishing of this local cohomology module used to define another fundamental invariant, which is called the Kostanov-Mumford regularity. So consideration of all these facts, it's quite natural to expect that all this behavior carried out by local cohomology modules supported on any arbitrary homogeneous ideal I. But on the contrary, it is known that that is not true in general, not even over polynomial ring. So let's look into an example. Let T be a polynomial ring over a commutative Noetherian ring A in two variables. So we are considering the ideal to be generated by the single variable x. Then the first local cohomology module of T supported on x, its evaluated components are free but not finitely generated. So it's not only contradicting the first one but also the second one, because it does not vanish for large values of U. So here I also want to remark that since T plus and I both are graded, so there is a natural induced grading on these local cohomology modules. So they are graded modules here. Hutun Purakar studied these local cohomology modules, and he observed that they are particularly well behaved under this setup. So he considered a standard graded polynomial ring over a regular ring containing a field of characteristic 0, and considered I to be an arbitrary homogeneous ideal in R. He mainly studied the asymptotic behavior of its graded components. And here, actually, as I have stated at the beginning, that over regular ring, local cohomology modules have certain finiteness properties. So it is quite natural to start with a polynomial ring whose base ring is a regular ring. And we extended some of these results to the case where R0 is any commutative Noetherian ring containing a field of characteristic 0. So throughout this, I will be referring this as setup 1, I mean as S1, and to be set aim to be the ith local cohomology module of R with supported on I. And here also I want to point out that over singular rings, all those finiteness properties generally does not hold. So, and we are in a situation where the ring need not be regular. So let's move to our results. So let J be an ideal in C and L is an SC module. Then it's well known that the jth local cohomology module of L supported on J, they vanishes for all J strictly less greater than the dimension of the module, and for all J strictly less than the grade of the module with respect to the ideal J. But it's very difficult to say whether the local cohomology module vanishes if J lies in between this grade and the dimension. In fact, I.G. MacDonald, he proved that if we take such a sequence n1, n2, 2, ns, an finite increasing sequence of non-negative integers, then there exists a certain local ring an0 such that this is depth of A, this is dimension of A, and the ith local cohomology module of A, this does not vanish only when I is some nj. So we can take any arbitrary sequence and we will get some local ring like this. So some algorithm, Lubeznik and Walter, they produced some two different algorithms to test whether this local cohomology module vanishes when both L and C are polynomial ring in n variables and their prime characteristic and characteristic 0 respectively. So here I also want to remark that the problem, there is something called, some invariant called the cohomological dimension, which is defined as the highest integer j such that the local cohomology module of some module does not vanish, but the cohomological dimension also can be determined as the least integer j such that the ith local cohomology module of the ideal I of R that does not vanish. So that reduced to the situation that to compute the cohomological dimension, actually we have to check that whether the local cohomology module of R vanish or not. We don't have to check for any arbitrary module. We just have to check for local cohomology module of the ring. And so it reduced to this situation, but even then there is no known algorithm to compute that cohomological dimension, and cohomological dimension has several interesting applications. We know that an ideal and its radical can't be generated by fewer number of elements than the cohomological dimension. There are several other applications. So several authors have studied this cohomological dimension, but till now there is no known algorithm. Only known situation is these two, where for the characteristic 0 case there is some algorithm and the computer algebra package Macaulay 2 has it has been implemented in the computer algebra package of Macaulay 2, but this characteristic P algorithm has not been implemented yet because of its complexity. So all this says that how much difficult it is, and this problem is quite interesting to find. And what we get, we showed that this local, if evaluated components of this local cohomology module, it vanishes for all sufficiently large values of u and sufficiently small values of u, then the module vanishes. And what it says that if a local cohomology module is non-zero, then it's either its evaluated component is non-vanishing for infinitely many small values of u, or its evaluated component does not vanish for infinitely many large values of u. Now we move to the tameness property. So let T be a standard gated Noetherian ring and L be a finitely generated T module. Then we say the module L is tame if there exists some integer u0 such that its uth graded component vanishes for all u less than equals to u0, or else it does not vanish for all u less than equals to u0. Broadman and Hillas, they raise the most challenging question regarding the asymptotic behavior of this local cohomology module, which is known as the so-called tameness problem. And they asked whether this ith local cohomology module of L supported on this irrelevant ideal, whether this is tame. And there are some affirmative answers known, but for many particular cases when I is the cohomological dimension, or for the case when the base string T0 has small enough dimension, I mean dimension is less than equals to 2, for those cases some positive answers are known, but Kartkowski and Harjo, they produce an example to show that they need not be tame even if dimension of T0 is 3. And we found an affirmative answer to this result for under our setup. I mean, when this L is the ring and T plus is any arbitrary homogeneous ideal, but for the case when R is a polynomial ring over any commutative Noetherian ring. I mean, that is not any standard gated Noetherian ring, that is the polynomial ring case. So there we found that if its uth graded component is non-zero for infinitely many small values of u, then its uth graded component is non-zero for all u less than equals to minus n. And if its uth graded components are non-zero for all large values of u, this happen if and only its uth graded components non-zero for all u greater than equals to 0. And just we saw from the vanishing theorem that if the module is non-zero, then one of these two cases will occur. And from the equivalent condition, we can see that they have the tameness property. So here I also want to highlight that for the tameness, here we only need to check in the negative direction. I mean, for all u less than equals to u0, I mean, only we need to check the first one. But that questions arise for the case of irrelevant ideal. And the example I have shown at the beginning, there we have seen that when we are considering some local cohomology module supported on arbitrary homogeneous ideal, in that case, for large values of u also, the graded components may be non-zero. So we need to study in the positive directions also. That's why we have considered the second case. And the second case also does not hold if we are in an arbitrary standard gated ring. I mean, in the paper of Kartkowski and Harjo, they gave an example of a standard gated Noetherian ring whose base ring is normal, three-dimensional, non-regular, and there with respect there is a, I mean, this T0 is a local ring whose maximal ideal is n. Then this 2 fails to hold for the ith local cohomology module of T supported on the extension of this maximal ideal. We further observe that the vanishing of a single graded component that behaves very strong, I mean, that has very strong effect on the local cohomology module. So let me explain this result through a figure. So what it says that if some r graded component of a local cohomology module is non-zero, then it is non-zero throughout the region. If and some Eth graded component is non-zero for some s greater than equals to 0, then it is non-zero throughout the region. And if some T graded component is non-zero for some t lies in between minus n and 0, then it is non-zero throughout the region. So here note that this n is the number of variable of the polynomial ring. So from this result, we can see that we can say all non-vanishing components, the graded components of a local cohomology module by only viewing the components minus n, 0 and minus 1 when n is greater than equals to 2. Because minus 1 will deal with this situation. So only seeing the non-vanishing of 3 graded components, we can see whether the other components vanishes or not. And this further says that whether a local cohomology module is 0 or not, that for that we only have to check its 0th graded components and minus nth graded components are 0 or not. So this is also a good criteria to check the cohomological dimension, that we only have to check that these 2 graded components, although there is no algorithm to compute through some computer algebra package, but at least we can, I mean, this is some simpler situation we can check. Now let me move to the techniques we have used, and that will help me to outline some proofs of some of these results. Let S be a polynomial ring over a field K. Dk's denote the K-linear differential operators on S, and A and K denote the nth Weyl algebra over K, where this dou I is the partial derivative with respect to I. Here this curly bracket indicates that this is a non-commutative ring, and indeed it is so, because for any I and j, the pair xi xj and dou I dou j, they commute with each other, but xi dou j, they will commute only when I not equals to j. And that is clear since this dou I is the partial derivative. And if characteristic k is 0, then it is known that this k-linear differential operator is isomorphic to this nth Weyl algebra. So any module over this ring of differential operators is known as the D module, and an interesting application of this module is, the main interest of D module is its approach towards the partial differential equations. So what it does, actually, if we take some set of differential equations, and then if we want to find, sorry, let me write here. So let us take some differential equations P1f, PTF equals to 0. Then there the solution space, I mean the polynomials, the k vector space of the collection of polynomial solutions, that means when f belongs to this polynomial ring kx1, x2, xn, then that solution space is isomorphic to form of A and k quotiented by this ideal and S. So this is neither an A and K module nor a S module. This is a K vector space, and this is the solution space of this set of differential equations. So thus this D module theory has an application towards the system partial differential equations. I mean, we can study via this. Okay, let's come back to our main topic. So, and we use this theory for our study. So here, now let for each nu greater than equals to 0, P nu be the K vector space generated by the set x alpha dou alpha, where mod alpha plus mod beta is less than equals to nu. Here x alpha denotes x1 power alpha 1, xn power alpha n, the product of these variables, and mod alpha denotes the sum of these components, these tuples. So here one can easily see that this T0 is K, T1 is the K vector space generated by x1, x2, xn, and dou1 up to dou n. So it is also easy to see that they form an increasing sequence of finite dimensional K vector space, and their union gives us the whole ring, this whole Weyl algebra. So this filtration is known as the Bernstein filtration on A and K. Now, if we consider some left A and K module M, then a filtration on this module consists of an increasing chain of K vector spaces which satisfies the inclusion Tk gamma nu contained in this gamma k plus nu for all pairs k and nu greater than equals to 0, and their union again gives us the whole module M. Now take the direct sum of these components and create this associated graded ring corresponding to this Bernstein filtration, and take the associated graded module corresponding to the filtration gamma. One can check that this is a graded module over this associated graded ring, and it is known that the associated graded ring is a polynomial ring in twice n variable over K. So this is the surprising fact, because here A and K is not Noetherian, whereas its associated graded ring is not commutative, where this associated graded ring is commutative ring. So we can use techniques from commutative algebra to study this non-commutative ring. Now, if M is finitely generated, if and only if there exists some filtration gamma such that the associated graded module is a finitely generated module over this associated graded ring, and such filtration is called good filtration. And one can check that if we are taking two good filtration, there is some containment among them. So if we take the Krull dimension of the associated graded module over this associated graded ring, then this remains constant under these good filtrations, and we denote this constant, this constant number as the Bernstein dimension of the module M. Since this is a polynomial ring in twice n variable, we all know from the theory of commutative ring theory that this dm should lies in between 0 and twice n. But surprisingly, it was proved that if m is a finitely generated non-zero module, then this Bernstein dimension lies inside n and twice n. And a finitely generated ANK module M is called holonomic if its Bernstein dimension attains this lower bound. Now let's look into some examples. Clearly the polynomial ring is a holonomic module, and it can be proved that the Bernstein dimension of this quotient ring where J is a non-zero ideal that is less than or equals to twice n minus 1. So in particular, if we take n to be 1, then this Bernstein dimension has to be 1 if J is not a proper ideal. So this is always holonomic, but this is not true for n greater than or equals to 2. And clearly an is not holonomic since its Bernstein dimension is twice n. Now Lubeznik proved that the ith local cohomology module of S is a holonomic ANK module. So here I want to remark that holonomic modules are not only finitely generated, they have finite length and they are actually cyclic modules. And mostly this is the first application of D-module theory in commutative algebra. From then this D-module theory has been used in different aspects like tight closure theory, that F jumping coefficients, and many more commutative algebra contexts. Now consider standard grading on S and ANK. That means we are taking degree of xi is 1 and degree of y is minus 1 and degree of all elements in K to be 0. Now we know by classical Euler formula that summation of xi y into f, that is same as degree of f into f for each homogeneous polynomial f in S. So inspired by this, Ma and Zhang, they introduced a class of graded D modules which is called the Eulerian modules in both characteristics. So if the characteristic of the field is 0, then we say a graded left ANK module L is Eulerian if each homogeneous element satisfies this equation. So here eta n is the Euler operator which is summation of xi to y, and by mod y we denote the degree of y. Notice that this Euler operator has degree 0. Again, let's look into some examples. So Ma and Zhang, they proved that this local cohomology module is Eulerian, and if we take any quotient ring, then it is Eulerian if and only if this Euler operator lies inside J. So more generally, they proved that any module is Eulerian if all generators of a generating set satisfies this equation. So here the generator is 1 bar, and clearly that will satisfy the equation if and only this Euler operator vanishes in the quotient ring. That means if it lies inside J. And due to the same reason, A and K is not Eulerian since this is non-zero. One does not satisfy this equation. Eulerian modules need not be holonomic even if we consider some cyclic modules. So for example, if we take this module, clearly this is Eulerian, but this is not holonomic for n greater than or equals to 2, because in that case its dimension is twice n minus 1. So, and also we can see that if n is 1, then clearly this module is holonomic. In fact, we know much more. If n is 1, then any finitely generated Eulerian modules are holonomic. So why so? Because any finitely generated Eulerian module, any homogeneous component is annihilated by the non-zero element x1 do 1 minus the degree of the homogeneous element from A1k. That comes from the equation. So that means this is a torsion module, and we know that any finitely generated torsion A1 module is holonomic. It is also known that any holonomic modules are torsion module for n greater than or equals to 2, but they need not be but the converse is not true. Any holonomic modules are torsion modules, but torsion modules need not be holonomic when n is strictly greater than 1. But the issue with this class of module is that they are not closed under extension. For example, if we take the short exact sequence, then one can clearly see that the modules on the sides, they are Eulerian, but the medial one is not Eulerian, since this Euler operator does not lie inside this ideal. To rectify this problem, Puth and Purakal introduced a new notion, the notion of generalized Eulerian modules in characteristic 0. So we say a module N is generalized Eulerian if for each homogeneous element of the module there exists some positive integer A such that it satisfies this equation. Here this A depends on Y. So again this quotient ring is generalized Eulerian if this some power of Euler operator lies inside this ideal J for some A strictly greater than 0. Here notice that if A is not equals to 1, then this is a generalized Eulerian module, but this is not a Eulerian module. Now let N say denote the nth Euler algebra over C and observe that this can be obtained by tensoring C with the nth Euler algebra over K. Since C is Noetherian by a non-commutative version of Hilbert-Bess's theorem, one can show that this nth Euler algebra over C is also Noetherian. So if we take C to be the power series ring in D variables over K, where K has characteristic 0, then any finitely generated non-zero AN DKC module that is holonomic if it has dimension D plus N. Actually, here also we can get some some filtration like Barstein filtration, and then we will get some polynomial ring which has dimension twice D plus N. Sorry, D plus twice N. And its dimension will lie in between D plus N and D plus twice N, and it will be, we say it holonomic when it has dimension D plus N. We can consider grading on A and C by defining degree of small c is 0 for any element small c in capital C, and degree of xi is 1 and degree of dou is minus 1. Then Puth and Purakal proved that this ith local cohomology module of R is generalized Eulerian ANC module. So here C is any commutative Noetherian ring. And this is the crucial result that we will be using later on. And he further proved that if C is the power series ring over K in D variables, then this local cohomology module is holonomic. So in our setting, although we don't have the notion of holonomic modules, but we have this notion of generalized Eulerian modules. And it appears that, under a little care, all these important results are carried over this generalized Eulerian modules. Now we are in a situation to sketch proofs of our results. So let's first talk about some properties of generalized Eulerian modules. So ANK module, then for all mu greater than equals to 1, this nth Dirham cohomology module of M with respect to dou n with the shift -1, this is a generalized Eulerian AN minus 1K module. The nth causal cohomology module of M with respect to this variable xn, this is a generalized Eulerian AN minus 1K module. And if we take n to be 1, then this Dirham cohomology module is concentrated in degree -1. And if we take n to be 1, then this causal cohomology module is concentrated in degree 0. That means there are only 0th graded components and -1 graded components are non-zero. All other graded components vanishes. So these results were proved by Puth and Purakal and Jyoti Singh, but they proved when. Sorry, actually here is some typos. I meant this K should be actually C, any commutative Noetherian ring. And when C is the field K, then it was proved by Puth and Purakal and Singh. But we observed that in that proof they have not used any properties of a vector space. So the same proof can be imitated to prove this. Prove the result in the general setup when C is any commutative Noetherian ring. And these are typos, this should be C. And also here I want to remark that any graded module can have only one particular shift which is generalized Eulerian. Just like that here I have mentioned that under this shift this module is generalized Eulerian. If we just take the Dirham cohomology module without the shift, that is not generalized Eulerian. To prove this result, mainly we have used the definition of generalized Eulerian modules, the relation that dou n xn minus xn dou n, that is 1, and the relation that eta n is eta n minus 1 plus xn dou n. Notice that this eta n minus 1, this is the Euler operator over a n minus 1 k or c. And the fact that xn dou n commutes with eta n minus 1. Now let ANC module, as we said, N1 to be the collection of all elements in N which are annihilated by some power of dou N, and N to be the collection of all elements in M which are annihilated by some power of Xn. Then we prove that this N1 into both are ANC submodules of M, and N1 is dou N N1 and N2 is Xn N2. They are same. So again, to prove these results, we have used these relations and we further use some induction hypothesis on T. So here notice that this is nothing but the zeroth local cohomology module of M with respect to dou N, and this is nothing but the zeroth local cohomology module of M with respect to Xn. So it says that both those local cohomology modules are ANC module. Now let us consider that R be the polynomial ring over C in n variables x1, x2, xn, and W be the polynomial ring over C in n variables d1 up to dou n. If I is a homogeneous ideal in R and J is a homogeneous ideal in W, then we can show that this gamma I of M and gamma J of M, they are ANC modules. So this is kind of the generalization of the previous lemma, because there we only considered I to be xn and j to be dou n. Now in particular we can say that this gamma x of n and gamma dou of n, they are ANC modules. To prove these results, we have used this fact and the chain rule to show greater than for all y in A. So then if I m, then it must vanish for some power t of I, then this 2 will vanish. So it will give us that this
Looks like she got disconnected or something.
Yeah, so I was wondering if I got disconnected.
No.
Yeah,
So,
but
yeah,
she's gone.
yeah. We can
We'll
wait
wait.
for some time.
Yeah.
Maybe we have time. Let's see, 4. Does Parangama or somebody have her phone number?
I have.
Could you call her? I don't have. Could you call her and check?
Yeah, sure. I will do.
Yeah.
She cut the call.
Unable to join now?
I don't know. She cut my call. So I
Oh,
don't
maybe she's trying to connect to the call and probably
Yeah,
put it.
probably.
Yeah, okay.
Yeah, she's joining. She just messaged me.
Okay.
So, Parangama, are you able to talk to her, or did you get any
No,
message?
she
Krishna,
said
she's
that if
saying
I call
somebody has to allow her to get in.
Okay, that is, I see, but that's not the case. So I have removed that. So
she
anybody
said
can join.
if she gets called, then she that there is a need if she's getting called at that time.
Sorry, what did you say? If she's getting a
Yeah.
call?
If I call her, so
Yeah.
there's some net issue with
Oh, I see. I see.
simultaneously calling and.
Okay, but there is no permission to join this meeting because anyone can join. So I don't know why she is facing the difficulty.
Anyway, I will email her because I think maybe she has difficulty in attending a call and she's trying to join. So just give me a minute.
I see. Okay, yeah.
Yeah, it only says enable waiting room, but it seems it seems not enabled. So it's not clear why. So anyway, just. No, maybe it's a. So she sent another email. She's just saying. She's saying just it is not connecting. It's just showing that it is connecting, but it's not going through.
I see.
So I don't know. Maybe it's some network speed issue.
Yeah, it can be any of those. Yeah, because it probably needs.
Maybe we can reschedule this some other
what
time.
we can maybe we can tell her that we'll just reschedule the talk and she can give a talk. I mean, she can give the full talk again some other time.
Yeah.
I will just I'll talk to her and then we schedule a suitable time.
Yeah.
Okay. So okay, then I'll then end this
Okay,
call.
so then we'll just end this thing. Okay, so we'll Suratu will meet that time. I mean, we'll continue with this.
Yeah. So we'll announce it again so people can join. Yeah. Okay then. So bye.
I mean, there was no 40-minute cap on this, right?
Yeah. So today I'm licensed. So.
Yeah, I suppose. I mean, we are sitting here for more than 40 minutes, so that could not be the issue.
Yeah. There is no. That is correct. Yes, that is one thing. But also, I have to make sure that I get a license today for this talk.
Yeah. Okay.
Okay then. So I'll end the call now. I'll write to her. With,
yeah.
To reschedule. Yeah. Okay.
Yeah.